Namaste. All right, good morning, guys. For today's lesson, we're starting something completely different. We're done with gravity, all right? And we're going to move into a unit called simple harmonic motion. And I wanted to start off this unit with just a quick lesson and some notes on the concept of springs. Okay, simple harmonic motion, what we'll get into this is motion that repeats itself. All right, so a pendulum going back and forth, the motion swings back and forth, it's repetitive. And the old word for that is harmonic. Okay, springs will do the same thing. For those of you guys who they go back and forth, when you stretch them, they kind of oscillate up and down or side to side, as the case may be. And for those of you guys who are going on to be engineers, really pay attention to this. Why? Because almost every single machine we make is cyclical. It's a cycle, all right? An engine or something like that, the compressor in your refrigerator, that sort of thing. And it's usually some form of spring that resets the cycle in the machine. Okay, for those of you guys who are going on, you juniors who are going to take the AP course next year, pay close attention to simple harmonic motion because it is so important in physics. Like the AP exam loves to give problems on simple harmonic motion. All right, so make sure you guys in particular are paying real close attention to this and know this. You engineers, you're gonna make a livelihood off of this type of physics, among others. So make sure you guys know this stuff. It's essential for your living and for your upcoming major and for the AP kids. It's essential to passing the AP exam. All right. Okay, so what is a spring? Well, you guys know what that is. It has different forms, but usually it's a flexible piece of metal. Okay. Sometimes it's coiled up. It doesn't have to be though, but oftentimes it's a piece of metal because metal has what's called elasticity to it. So if you disturb it, you bend it, and then you let it go, right? It'll go boom back to its original position, okay? And so we say that property is elastic. That's opposed to something like, Play-Doh or putty or clay or something that if you take it and you bend it back, it just stays back like that. That's not elastic, okay? So let's take a look at this for a second. Let's get some language down. All right, so draw this out in your notebook, but let's say this is, I don't know, like some sort of ceiling or something like that. We're going to put a spring on it. Okay, so here's the spring right there. We're just going to let it hang. Okay, and let's say this position right here, that if you let the spring alone and you just let it hang and it just stayed right there, we would say this is the equilibrium position. And we give that position the variable x naught. Okay, or starting position. I'm not going to write it down on the board for lack of board space, but know the word equilibrium position. It's the place where the spring wants to be if you just leave it alone. Okay, now let's say that I take the spring and I pull it down. So now the spring looks stretched out like this, and now the end of it is down here. So it started up here at x naught, and now it's stretched, okay? And so we say that it is stretched some displacement, and notice I'm using the word displacement, not distance, because the direction matters. All right, and it has stretched out some displacement delta x. Well, when you do that, if you stretch it out, the spring automatically produces a force against you pulling it from its equilibrium in the direction that's opposite direction you're pulling it. And you guys kind of know this, right? So the spring is going to pull back with the force of a spring, and I'm going to put a little s there, all right, in the opposite direction. And you can do the opposite with springs too. You can compress them, okay? So you can, let's say I push the spring up like that, and now it's kind of squeezed up like that, all right? And here's where it wants to be, but I pushed it up. So now the spring is pushing back in this direction. Here's my displacement in this case with a force of a spring, okay, Fs, and that force would have changed direction. All right, so just so you have that. Okay, now, if you were to graph this, okay, so if I were to take the spring and pull a little bit, and then measure the force that the spring pulls back on me for pulling it a little bit, and then I pull it back some more, and the more you pull on a spring, the more it pulls back on you, okay? and if I pulled on it a little bit more, it will pull back on me more. If I pulled it more, it would pull back on me more. If I were to graph this, okay, I would get a graph that looks something like this. Okay. Sorry, that's my eraser over here. And I want to get a graph that looks something like this. So if I graph the force of a spring up here versus delta x, okay, what would happen is I would get a straight line for any spring. Up until the point where, and now if you're an engineer, we don't get into this in this course, but if you're an engineer, you will, okay, up until the point where the metal starts to distort, and then it would do, you know, something like that or whatever, and whatever, you know, but we don't handle that in this course. Suffice to say, in this course, if you would do it, you would get a straight line. Well, what's the equation for a line? Well, y is equal to mx. The y-intercept would be 0, because if you didn't disturb the spring at all right, and we'll say x naught is 0, then it would just be at its equilibrium position. It wouldn't pull back on you, it wouldn't push on you at all. All right, so the y-intercept is 0. Well, instead of a y, we have the force of a spring. And instead of an x, we have a delta x, or displacement vector. And instead of the letter m, which we tend to use for mass, we're going to write the letter k. Okay? And this k has a special name. We call it the spring constant. Okay? Now we're going to slap a negative sign on it right now. Why? Because the force that the spring pulls back on you is always opposite the direction that you stretch it. Remember, this is a displacement vector. Why? Because it matters which way you pull it. It matters whether you pull the string one way, we'll say that's positive, or you push the string, compress it, we'll say that's negative. But whatever way you pull it or push it, the force that the spring makes is opposite that direction. Okay, so we're going to slap a negative sign on it. Now this equation, now I hope you recognize that you've seen this process before. We did it when we did friction, the force of friction, okay, on an object versus the normal force. And then we did a graph and we made a line, and we said that that constant was called the coefficient of friction. Okay, with a spring we say it's the spring constant. Okay, now anyway, so this equation, negative kx, the force of a spring, is equal to negative k delta x. Now you could actually pretty much write x, because x naught is usually 0, okay, for the most part. All right, this has a name to it, and it's called Hooke's law. Okay, named after Mr. Hooke. All right, physicist who studied springs and so on and so forth, and came up with the equation. All right, okay, important to note. So let's take a look at the spring constant. K, if you were to solve for it, K is equal to, now I'm going to take the absolute value here, okay, would be equal to the force of a spring divided by the distance that you stretch it. And so the units on that would be units of, well, with force it's newtons, divided by distances in meters. So it's newtons. So the units on the spring constant are newtons per meter. Okay. Now the spring constant, like the coefficient of friction, is just it's a number that tells you something about the spring. The bigger the number, the stiffer the spring. Okay, or the stronger the spring. Sometimes you want a weak spring, like in, you know, your pen when you click it, there's a little spring in there. You don't want a strong spring in that. You just want a small one. Sometimes you want a very strong spring, like in the suspension of your car. Obviously, in order, you know, you have a car with a lot of weight on it, and you're trying to dampen the bumps in the road so that you don't feel as much while you're driving. So you would want a very strong spring. So in there. So for example, 3 newtons per meter would be a weak spring, and 3,000 would be a strong spring. Okay, so similar to coefficient of friction, where the smaller the coefficient of friction, the less friction you have between two surfaces, and the bigger it is, the more you have it. Okay, all right, so just wanted to make sure that you guys had that language. All right, okay, Now, let's go into this a little bit, and let's get a little more advanced, and let's talk about Newton's second law of motion, which says that F equals ma. Okay, so let's say that I have a situation like this, all right, and so here's, I don't know, like some sort of table or something like that, and actually let me do this, okay, whatever, and okay, so I have a spring here, and let's say that this is like the equilibrium position right there, x naught, we'll say that's like 0, and so what I'm going to do is I'm going to put a spring on here, okay, attach it to the wall, I'm going to put a mass on it, as Grandma Golis would say, like so, and I'm going to compress it. And what would this do? Well, I'm going to compress it some distance, delta x, and if I let it go, the mass would, the spring would force it forward, and the mass would go like this. It would go, its inertia would take it past the 0 point, and would go to like an equivalent position over here, say, and then it would oscillate back and forth, neglecting friction. Obviously, if you had friction there, it would stop eventually, so it would go back and forth and then slow down and stop. But let's say that there is no friction. If there is no friction and you did this, then it would just keep going and oscillating back and forth forever, okay? So let's say that's the case. Well, if it is changing, if it is oscillating back and forth, that means it's changing its speed, because over here at the endpoints, it's 0. And over here in the center, it's moving its fastest, similar to a pendulum. All right, when you have a pendulum like that, okay? So here's the endpoint of a pendulum. Here's the other endpoint. It's slow and stops over here for an instant as it changes direction. And then at its lowest point, it's moving its fastest, and so on and so forth. Okay, so it's an analogous situation right here. Now, if it's changing speed, then there's an acceleration involved. All right, so let's take a look at that. All right, so Newton says that that a force, a net force of a spring, in this case, is equal to ma. Well, we know that that's equal to negative k delta x. Okay, all right. So what does this mean here? Well, what this means is this, and here's how we interpret this. Okay. What this means is that the acceleration, unlike when we were dealing with gravity or kinematics problems, let's say when we did kinematics problems, we had a car speeding up or something like that, we would say that the acceleration is constant. In this case, the acceleration is not constant. It's constantly changing. You have a changing acceleration here. So the acceleration, A, is not a constant in this case. And in fact, there is a point where the acceleration is actually 0. Where would that point be? Well, at x naught, the equilibrium position, which is usually taken to be 0, the acceleration is 0. Why? Well, look at the equation. All right, when the mass gets to that equilibrium point right there, where it actually happens to be moving the fastest, x is 0. If x is 0, that makes this side of the equation 0. Well, that means this side of the equation has to equal 0. Well, m isn't going to equal 0, but a will. So the acceleration at the equilibrium point is actually 0 for an instant. Just an instant. Okay? All right, and make note of what I said. Now, we were in class. I'd spend a little more time on this, but I'm doing a video, so I can't. All right, so I'm moving kind of fast, actually, faster than I should, but anyway. So, and what winds up happening is, okay, the acceleration is actually a maximum at the endpoints. Now, what happens at the endpoints, what's interesting is at the endpoints, V is 0 at the endpoints. That's the point where it stops going to the right and slows down, stops going to the right, and then turns around. You have had experience with this in the past when we have taken a ball and you throw the ball up and there's its highest point, and then it goes back down again or something like that. All right, so even and when you throw a ball up, and this is something that some of you guys had to kind of like ponder about, is when at the highest point, when you throw a ball, it's the changing point. It's where it stops going up, starts coming back down. And the velocity at the top for an instant is 0. But is it accelerating? Yes, it is. Because it's only at that velocity. It's only at that point for an instant. It's passing through 0. Remember, that's the sophisticated meaning of acceleration. All right? You're passing through velocities. And 0 is just another velocity. Okay? Just like 1.3 or 1.426. Doesn't, whatever. It's just one velocity out of an infinite number as it's changing velocities. Okay? So something to note there. All right. Okay. Now let's go back to that graph. Okay, so here's the force of a spring, and here's delta x. And so here we have this again, right? So let's say that we pull the spring back to its maximum distance, and we will call this maximum distance A, okay? Oftentimes called the amplitude of the oscillation, all right? Yeah, learn the language on that and listen to how I'm speaking, okay? Now, this is why we taught you graphical analysis in the fall, because we can get some information from this graph. So if you take a look, and we would do the area under this, okay? For those of you guys who took calculus, we'll say the area under the curve. For those juniors who are going to take calculus next year, the area under the curve, even though it's really a line, doesn't make a difference. All right. Now it's a triangle, so the area would be 1/2 the base times the height. Okay. And so in this case, the area, what would that represent? Well, that would be 1/2. Okay, and instead of the base, I'm going to write the height first, the force of the spring times delta x. That would be the area underneath this triangle. Well, let's take a look at that, all right? And we're going to do some unit analysis, which is, again, something that, the reason why we taught you this at the beginning of the year. Let's see what the units of this wind up being. Okay, I'm going to substitute fx for 1/2. Now I'm going to use the absolute value, k delta x, because this is the force of a spring, times delta x again, okay? Well, this winds up being 1/2 k, the spring constant, delta x as a quantity squared. Now, if I do unit analysis on this, k has units of newtons over meters, and then what I have is meters squared for the delta x squared, so it's meters squared. One of the meters down here goes with the meter down here goes with one of the meters up there, and that leaves me with units of newtons times meters, which is a joule. All right, a joule is a newton times meter. That comes from the work equation, F times D, newtons and meters. Well, work is a change in energy, and joules measure energy. So what would this quantity represent? This quantity under here represents the potential energy. Well, what it will represent would be the work, the energy you put in to stretching the spring to that point. Now, okay, well, what type of, at that point, right, when you stretch the spring, stretch, when you're at that point A, when you stretch it out that point, if you let it go, it has the potential to move. So we would say that that energy in here, that energy that we would calculate would be the potential energy of the spring, okay? So now in this case, it's not gravitational, which is mgh. It would be elastic potential energy, okay? The potential energy that is stored in an elastic object, so that when you distort it and then you let it go, the energy it has in wanting to go back to its original position. So the energy involved of a spring, the potential energy of a spring, U for a spring, is 1/2. Now it's irrespective of direction. So I'm going to drop the negative sign. So understand that, because that bothers some people. Okay, it was like, where's the negative? And it's negative, and it's like, yeah, let it go. Okay, all right. It's irrespective of the direction, so we'll just drop it. But the potential energy of a spring is kx squared. Technically, it's delta x. You can put that in if you want, but we'll assume that the spring is starting from a 0 point. Okay, so x minus 0 is just x, so we'll just leave it like that. The maximum potential energy is 1/2 k a squared. Okay, where this would be the amplitude of oscillation of the spring in the system that I just showed you, where you had a mass going back and forth. Okay, all right. That's enough for now. I just did a 20-minute video and I meant to do a 10-minute one. So I'll leave it at that. But make sure you're taking notes on this because you're definitely going to need this. Okay? All right. Goal us out and enjoy your apocalypse.